look at this wavelength. This just says wavelength, but there's going to be a certain wavelength in the air, or this material 1. I'll call it lambda A. It could be air. It could be, I don't know, anything out here that light can travel through. And then it's also going to have a certain wavelength in the oil, and the wavelength in this oil is going to be different. I'll call this wavelength B. It's going to be different from the wavelength in this first material if the speed is different. Shoot, it could even have a different wavelength in the water, but we don't worry about the wave traveling down here, so let's not confuse ourselves. Some of the light will pass through here, but it's not necessarily going to get back to my eye, so I'm not going to worry about this part. How do we find, first of all, which one do we use in this condition? Do we use the wavelength in the first medium, A, in the air, or do we use the wavelength in the oil? Well, we use the wavelength in the oil, most definitely. We use always this wavelength here. Both of these are always the wavelength in the thin film. So the wavelength the light had in the thin film, because that was the portion of the path where the light traveled an extra distance. So that's the part that will matter. We want to know how much further up, if the light that reflected, if this first light ray when it reflected was right here, we want to know where's this other one going to be at when it emerges. Because if it emerges also right at that point, say this wave over here, this wave cycle, say it also emerges exactly at that point here, well, they'll be constructive. But if it emerges over here, that's only 180 degrees, that's 180 degrees out of phase, then it'll be destructive. We want to know how much this cycle got progressed by this wave traveling through here, and so we need to know the wavelength in here. That's the wavelength that actually matters, wavelength in the thin film. Oftentimes, you're not given the wavelength in the thin film, you're given the wavelength in the air, or whatever this material is. So if you know this wavelength, how do you get the wavelength in the oil or the thin film? How do we find this wavelength? Well, it's not too hard. The most straightforward conceptual way to think about it is that, well, frequency doesn't change. The frequency in material A is going to equal the frequency of the light when it enters material B. Frequency is determined by the source. If it's the sun up here that emitted that light ray, or the laser, that's what's determining the frequency of this particular light ray, and that stays the same whether it reflects, whether it refracts, no matter what it does, frequency stays the same. That's a useful thing to know, and it's useful in this case because, well, how do we relate this to wavelengths? We know the speed of a wave equals wavelength times the frequency, and so if I wanted to solve this for frequency, I divide both sides by the wavelength, and I get that this is equal to the speed of the wave over the wavelength. So I can replace that over here. VA, so frequency in material A is just speed of the light in A, because of this formula, over wavelength of the light in region A. You think of A as air. It doesn't have to be air, but it could be. It was in this case. Frequency of the light in B, which is our oil, would be the speed of light in region B divided by the wavelength in region B. Okay, so now we can just solve for wavelength in region B, and we get that wavelength in our thin film will equal, I multiply both sides by wavelength in B, and then I multiply these out, and what you'll end up getting is velocity of the light, speed of the light in region B, divided by speed of the light in region A, that factor times the wavelength of the light in A. So this is one way to determine if you're given the speeds like I did here. Remember I gave you the speed of the light in the air. That you can look up because that everyone knows. You can look it up, it's online. And speed of the light in the oil, I just told you what that was. If you're given these speeds, take the ratio, speed of light in oil divided by the speed of light in the air, multiply by the wavelength in the air, this first medium, and you'll get the wavelength in the second medium, which is the oil. This would be what you'd plug into these formulas up here. What if you're not? Sometimes you're not even given the speed. What if you're given, sometimes they give you the index of refraction and you're like, index of refraction, shoot. Well, if they gave you the N in region A and instead gave you the N in region B, instead of giving you the speeds, remember, index of refraction is defined to be speed of light in a vacuum divided by the speed of light in that material. So NA, index of refraction of region A, is just 3 times 10 to the 8th divided by the speed in A. And NB would be 3 times 10 to the 8th over the speed in B. So how would this change? Well, shoot, I could just solve this for VA if I wanted to. I'd get VA, I'm running out of room here, excuse me, equals C over NA. And VB, what would VB equal? VB would equal the speed of light in a vacuum divided by index of refraction in B. All right, now imagine just plugging into here. I'm going to plug in VB, which is this, for VB. And I'm going to plug in VA, which is this, for VA. I'd get a new condition. What would that new condition be? That new condition would say that wavelength in B equals, well, look, C over NB is what I get. C over NB divided by C over NA from this condition times lambda A. I can simplify that. The C's cancel. And then 1 over NB divided by 1 over NA just gives me NA over NB times lambda in the air. So here's another one. Here's another condition, another way to find it. This would also equal the wavelength in the oil or the thin film. So if you're given the speeds, you can take the ratio of the speeds. You do the oil speed divided by the outside speed multiplied by the wavelength in the air. But if you're given the indexes of refraction, you take the outside index of refraction divided by the inside index of refraction times lambda A. You're thinking, oh my God, how am I going to remember all this? Here's how I remember it. I know if I go from air to oil, light's going to slow down. And if light slows down, frequency stays the same. So if light slows down, wavelength's got to go down. So I just look over here and I just make my ratio. If they give me n's, shoot, I just make sure my ratio of n's gives me a smaller number, a number less than 1 that I multiply by to get my lambda in the thin film. And if they gave me speeds, shoot, I just take my speeds. I take my ratio of my speeds so that I get a smaller lambda in the thin film. Just got to be careful. Make sure you're really slowing down. They might give you a problem where, for some reason, this wasn't air, some other material. It was going faster through the oil than it would be through here. Then you'd want to make this ratio more than 1 when you multiply. But if in doubt, you can always fall back on the 2 frequencies are equal and use that. And that's the 3 things you got to worry about for thin film. These are the conditions. Make sure you pay attention to whether there's a pi shift, and make sure you always use wavelength in the thin film. So if we wanted to, this looks messy. I'm sorry about this. This looks horrible. We could turn this all into one super duper equation. Let's do that. Let's get, I can't even look at that anymore. All right, let's do this. So we know, what do we know? We know for constructive, we should have 2t equals integer, so m is 0, 1, 2, 3, times the wavelength in the oil or the thin film, but I don't want to solve for that every time. We already did it. So let's just write this. We know velocity in this region is A. The thin film region we'll call B. Then we know that V in B divided by V in A times wavelength in region A, which is oftentimes the air. This would give you constructive. Or if you were unlucky and you got index of refraction, then you could use index of refraction in A divided by index of refraction in B times the wavelength in the A region, and that would be what you would need for constructive. We could do the same thing for destructive. 2 times t should be, well, half integers, so we could do m plus a half times this same thing, wavelength in the thin film, which again is VB over VA times lambda A, or same thing, half integers times wavelength. But if you had index of refraction, you'd want to use NA over NB, lambda A. This would give you destructive. Only other thing to worry about is if there's a relative pi shift. You would flip-flop these conditions. These half integers would give you constructive, and the integers would give you destructive if one wave, and only one wave, gets a pi shift. If one wave gets a pi shift, then you swap these conditions. This still looks a little bit intimidating. I'm sorry, that looks intimidating. So sometimes it gets even better. If this region A is air, well, the index of refraction in air is just 1. So that cleans things up a little bit. This just becomes 1. And this up here just becomes 1. So you end up with m times 1 over nb times lambda a. Or in other words, m times lambda a over nb would give you constructive, and m plus a half times lambda a over nb would give you destructive for every m equals 0, 1, 2, 3, and so on. 0? Can you really have 0? Yeah, you could. Kind of. I mean, if m equals 0, that would say the thickness is 0. Doesn't that mean you have no thin film? Well, sort of. But if this thickness is very, very small compared to the wavelength of the light, it's as if the thickness is 0, and that will give you either constructive or destructive depending on the pi shift. And sometimes you can do that. Anti-reflective coating is often just a coating that's so thin, completely thin compared to the wavelength of light, which just makes all the light reflect destructively, because in that case you do get a pi shift and these integers give you destructive points. So that's thin film interference. Sometimes confuses people. Hopefully you do well with it. These are the ways you deal with it.